All right, guys, I think we should actually get started with today's session. That was very kind of you. Omkar, maybe let's switch to the next slide. All right, folks, for those of you who don't know Interview Kickstart, we are a platform where you go to prepare for very tough technical interviews. We are a one-of-a-kind platform. We've been running this now for about 6 years, right? We created the concept of a very structured program to prepare for very tough technical interviews. We worked with over 4,000 students in the last 6 years. We've generated upwards of 5,000 offers. The median offer coming out of the program tends to be around $250,000. The core philosophy of the program is that you cannot really hack a technical interview. The only way to fundamentally be in a position where you can go out and nail these technical interviews consistently is by investing in yourself and becoming a better engineer, right? And that is what Interview Kickstart is all about. It's about taking folks who are genuinely interested in up-leveling in their career, folks who have very good intent, willing to commit the time to prepare for these tough technical interviews, putting them through a very structured process. We literally look at this as a system, have them work with folks who are experts on technical interviews. All our instructors, like Omkar, are folks who are either hiring managers, hiring committee members in many cases, very senior technical leads, but all folks who are very well versed with the typical interview process. They come from Google, Facebook, Amazon, LinkedIn, Uber. Fundamentally, these folks have done hundreds of interviews, right? They're all very well trained to interview at the companies that they work at. The heart of how we teach, and Omkar is going to showcase some of this today, is that we teach via patterns, right? Not via questions. Now, most people make the mistake of thinking that, hey, I need to do 100 questions or 200 questions or 300 questions, right? The number seems to keep going up every year to prepare for interviews. But the reality is, if you prepare via questions and you get a question that you've not seen in an interview, you're going to get stumped. What you fundamentally need to prepare for is to be able to solve unseen questions, right? And that is where patterns come into play. That is the heart of how we teach, and we follow a very rigorous system. We have classes, we have tests, we have mock interviews, we have a whole bunch of individual coaching sessions as well. We help you right from the time you prepare your LinkedIn profile, your resume, all the way up to teaching you, and in many cases, connecting you with companies as well. Now, I won't talk more about what we do on Interview Kickstart, because today's session is actually on graphs, right? But for those of you who are fundamentally interested in taking a very structured approach to preparing for technical interviews, one that has an extraordinarily high success rate, right? People who go through the program, choose to go out and interview, have a 95% plus chance, right, of getting their dream jobs. For those of you who want to learn a lot more, please go to interviewkickstart.com, sign up for a free webinar. I conduct these webinars multiple times a week, where we get into how the program works in great detail. The companies on the right here are where typically people go once they are done with the program. Now, let's get to today's session. Today's session is run by Omkar. Omkar, can you move to the next slide, please? All right, so, you guys can see Omkar here. You can see on the screen. Omkar is a fabulous instructor, right? He's been with IK for the last 1 year. Omkar actually heads all curriculum at Interview Kickstart. He has helped navigate the curriculum to now focusing on a much more patterns-based approach. He's the consummate nerd, right? And I say that with utmost affection. He is brilliant at what he does. PhD from Stanford in computer science. Prior to that, did his computer science engineering at IIT in India. He is a gifted teacher, and somebody who can take very complex topics and simplify them, right? What he's going to attempt to do today is provide a unifying theory, right, of how one thinks through graphs, which tend to be a very complex topic, and also a topic for those of you preparing for interviews that is very frequently asked, right? Prior to Interview Kickstart, Omkar was very early at Kosmix. Kosmix eventually got acquired and became WalmartLabs. When Omkar joined Kosmix, at that point of time, Kosmix was very well known for having amongst the best engineers in the Bay Area, comparable largely only to folks at Google, right? That was the early bunch of folks at Kosmix. Omkar also had a little bit of a gaming stint, right, where he built a game. But for the last 1 year, and I'd say this is Omkar's passion, he loves teaching, he loves taking complex topics, simplifying them, and is able to teach them with significant alacrity. With that, guys, I hand you now to Omkar's capable hands. Omkar, why don't you get started with today's session? The way we are going to run this session, guys, is Omkar is going to teach you, right, in an hour, his view of the unifying theory of graphs, right? Feel free to ping us with questions during the session. Omkar may look at the question from time to time if he feels. Otherwise, once we are done, right, with the hour, he will take detailed Q&A, right? And with that, Omkar, over to you. Let's get started on today's session. I hope you guys enjoyed today's UpLevel microclass. Cheers.
Thanks, Ryan. Good evening, everyone. So over the next hour, I will be sharing with you a glimpse of how we train our students to master graphs for technical interviews. I'm particularly pleased to be presenting this to you because there isn't much information available to the public about the high quality and the comprehensive nature of our curriculum. Much of the material that I'm presenting to you has been developed within the last 6 to 9 months. We are continuously iterating and innovating on all fronts as the demand for our program increases. I do want to emphasize that this is going to be a sneak peek, much like quickly scanning through some sample pages of book on Amazon.com. So let's begin. Let's start by confirming to ourselves that graph algorithms are crucial to learn for giving technical interviews at any of the top tier companies.
Omkar, this is Ryan. Can you maybe just come a little bit closer to the computer? I think it's the screen's a bit dark. Yeah, it's much better now. Sorry, go ahead.
So Google, for example, advises candidates that they should consider if the problem that they've been given in the interview could be solved using any of the standard graph algorithms. You should know what are the different ways to represent a graph in memory, their pros and cons, and specifically know in detail how to analyze and implement breadth first search and depth first search. Facebook says the same thing in a more condensed form. You should learn graphs, especially BFS and DFS. Amazon also recommends the same. Pretty much every top tier company expects you to know graphs when you interview with them. Since you enrolled for this microclass, you probably were already convinced about the importance of graphs. Still, if there were any doubts, what Google or Facebook or Amazon said should hopefully put them to rest. So how should you prepare well for a complex topic like graphs? Well, regardless of whether you're preparing on your own or planning to enroll in our program, you can follow the same structure that we do. This is the IK Graphs curriculum, shown as a graph mentioning the major topics and algorithms. I'm going to elaborate on this slide in more detail as we go along. Note for now that many of the topics are shown in green and others in blue. The green topics are the more basic topics and also more commonly asked in interviews. And so much of your focus in prep needs to be on the green topics. We devote about 10 hours of instruction for the topics in green and more than 8 hours on the advanced topics. So in total, we have more than 18 hours of live and recorded instruction on graphs. This is way more than the amount of time spent on graphs, even in an undergraduate university course. Why do we do this? It's because effective preparation for a coding interview is a combination of two things, both of which need time. First, you need to learn how to solve questions that you have not seen before. These are called problems, and problem solving in coding interviews means designing a correct and efficient algorithm that solves the given unseen question. And to do this, you need to understand the fundamentals of computer science theory and in the context of graphs, graph theory. And then you need to be able to draw upon it when designing algorithms using strategies like decrease and conquer, divide and conquer, and transform and conquer. And all this needs time, especially if you didn't go through a solid computer science program on your, in your education. Secondly, once you arrive at a correct and efficient algorithm, you need to be able to code it up relatively quickly in a way that your code will not have major bugs. When you're inside that room with the interviewer, your mind might be in a state of anxiety because the interview is, after all, a time test, and time tests always cause anxiety. So if you try to write code from scratch without having a template or pattern in your mind for how your code will be structured, chances are high that you will fumble and your code will have some major bug. That is why we train our students not just in problem solving, but also in solidifying those coding patterns, which remain the same across a wide array of problems. We do not move from one random problem to another in our prep. We follow a carefully laddered sequence of problems meant to solidify these coding patterns. So this makes our prep not only as rigorous as a top computer science course, but also specifically relevant for interviews. University courses and algorithms textbooks focus almost entirely on solving problems theoretically. So here's a snapshot from the slides of CS 161, which is the undergraduate algorithms course at Stanford. The purpose of such courses and of the textbooks is generally to turn you into a graduate student or a PhD student under that professor, or at least in that department. They generally don't think about how to make you succeed in coding interviews. That's not their goal. And that is why you may find the professor himself or herself copying code from prepared notes onto the blackboard, as in this example from MIT's course on algorithms. If you need written notes to write your code correctly in an interview, you're not going to clear that interview. Or the professor would directly put the code on one pre-written slide and explain it, as in this example from Bob Sedgwick's course at Princeton. Again, you will need to write code from scratch in an interview. So don't get me wrong, these are world-class professors who have made fundamental contributions to algorithms research, and their courses are excellent. You can and should learn theory from them, but you also need to learn the theory in a way that allows you to quickly code up solutions to problems from scratch using coding patterns in an interview. You can't look up slides or notes for reference in an interview. Also bear in mind that professors operate under time constraints in a lecture. They need to cover a certain amount of material within a relatively severe time limit, which means they may not be able to devote enough time in their video to show you how you could come up with the solution to the problem yourself, trying out different options and gradually building your way to the solution. Since we do that at IK, it also means that we need to spend more instructional time in the process. We can't just tell you the final solution. We have to show you how to arrive at the solution. So hopefully this clarifies why we spend more time on these topics in our courses than even a top university course. So if textbooks and university courses provide a decent amount of problem solving, but are not focused on coding interviews per se, what about LeetCode? LeetCode is at the other extreme. LeetCode is an excellent question bank of highly relevant interview problems, but it is a question bank. It's not a substitute for systematic and structured learning. Think, for instance, how much would you learn in a university course by directly attempting the questions from, say, previous year's exams without attending the lectures and without reading the textbooks? Not much. Similarly, you won't learn much by just attacking the problems on LeetCode directly. They don't teach you the theory, and the problems are not organized in a carefully laddered sequence. Moreover, the solutions to the problems are written by different people, which means you may not find a consistent coding pattern being used for different problems within the same category. Many people also tend to write micro optimized code, going way beyond the requirements for a correct and asymptotically efficient solution. And that also tends to hide the close relationship between different related problems. The code for different problems looks more different than it should because of these crowdsourced solutions and micro optimizations. Now, those will be useful if you're doing competitive programming and if you're already fluent with this domain. But we are talking about coding interviews for experienced software engineers here, not competitive programming contests for college students. So at the end of the day, what you want to do as an engineer is to understand how you can arrive at the solution to a given unseen problem yourself, and how to write sufficiently well-performing code for the most efficient algorithm from scratch. Seeing micro-optimized code written by different people for random problems can actually shatter your confidence in yourself and can drive you to memorize those solutions, making the entire interview prep process a lost opportunity to make yourself a better engineer. You would be more or less depending on luck to hack the test, hoping that you'll be given questions whose solutions you have memorized. And naturally, you'll have a brain freeze the moment you're given an unseen question because you didn't prepare for the worst case. So let's look at how we utilize those 18 or 20 hours to teach graphs. If you're planning to independently study graphs, you could follow this same sequence. Basic graph theory is a prerequisite for problem solving. So we spend the first module learning the basic terminology, concepts, and patterns of reasoning in graph theory, but not via a dry list of definitions, as is the way algorithms books and courses introduce the subject. Rather, we do this via the real story of the origins of graph theory back in the 18th century in the Prussian Empire, in the city of Königsberg, where in the midst of a booming economy, the residents construct 7 bridges across a river that flows through the heart of the city. Those 7 bridges are shown here in this Google Maps image. Every Sunday morning, as the residents took their morning walk, they were curious about the following question. Can one walk across the 7 bridges without crossing the same bridge twice? That is, can one walk across the 7 bridges, crossing each of them exactly once without repeating any bridge more than once and without missing out on any bridge? They were so intrigued by this puzzle problem that they took it up with the mayor. The mayor was not a mathematician himself, and so he wrote a letter to the most famous mathematician of that time, Leonhard Euler, requesting him to solve the problem. Euler did solve the problem and published the solution to the problem in a paper. And this is his original sketch in the paper, showing a specific section of the map of the city of Königsberg that has all the 7 bridges diagrammed. Notice that he represented each land area by a single letter, A, B, C, and D. That was his way of saying that it didn't matter what the shape of the land region is or what the size is. All that mattered is that there were these 4 land regions, A, B, C, and D. And they were connected using these 7 bridges. Again, it didn't matter what the length of each bridge was, what the width of each bridge was, where exactly they were located. All that mattered is that there were these 4 land regions connected by these 7 bridges. And so we can ignore all the other details. Now, this diagram, which Euler did not draw himself, but that's how we visually think about it today. This diagram can be shown in a slightly neater way. And it's what we know today as a graph. A graph is a collection of vertices corresponding to the land regions and a collection of edges corresponding to the bridges. And since these bridges were two-way streets, there were no directions on the edges. And so we call this kind of graph as undirected. 2 vertices are said to be adjacent if they are directly connected by a bridge. So vertices C and D are adjacent. A path in a graph is just a sequence of adjacent vertices. So D, B, A, C is a path. And a cycle is a path that ends at the same vertex from where it starts. So D, B, A, C, D is a cycle. So if we model the map of Königsberg with a graph like this, the problem that Euler had to solve was, is there a path in the graph that visits every edge exactly once without missing out on any edge and without repeating any edge more than once? And this is the well-known Eulerian path problem. Euler's answer for the specific graph of Königsberg was a no. That is, you cannot take a morning walk like that. But Euler actually ends up solving the problem for a general graph. Now, how he did so is what we cover in the first module of our foundation material. It takes more than an hour. So obviously it's impossible for me to do it in a session where I have to give an overview of all of graphs. So I can just summarize a few lessons from it. The first lesson, Euler shows us how he grapples with questions he has not seen before and for which he had no idea what method would work. He first tries a brute force approach, which he quickly discards as being too tedious. And then he tries to attack the problem using techniques from various subfields of mathematics from that time. And he sees that this can't be solved by any of those subfields or methods in those subfields. So his starting point is a state of feeling clueless. It's not as if he instantly solves the problem. And he was one of the most brilliant mathematicians in all of human history. Why should we expect that we will be able to instantly come up with answers? So feeling clueless when you're given a problem you haven't seen before is a natural starting state. The second lesson specifically applies for graphs. The classic sign that a given problem can be modeled as a graph is that you're given a set of topics, set of objects, and you're given a set of pairwise relationships between them. Pairwise relationships are a giveaway that the input to the problem should most likely be modeled as a graph. Lesson 3, it's extremely hard to invent a new graph algorithm from scratch. This means that in an interview, when you are given a problem that seems to be a graph problem, you should immediately ask yourself, how can I stand on the shoulders of giants to solve this problem? In other words, what standard graph algorithm am I going to use to solve the problem? I won't be inventing my own graph algorithm. I'll be using an existing standard graph algorithm. So you need to know which algorithm you'll use even before you have worked out the details of how to model the input, because which graph algorithm you plan to use will dictate the details of that modeling. So having learned the basic concepts, terminology, and historical origins of graph theory, we next teach our students how to model the pairwise relationships that I talked about as a graph. So when we talk about graph representations, we're really talking about different ways to represent the pairwise relationships or the edges of the graph. The vertices of the graph can be maintained separately, and we don't generally worry about that in a graph problem. Our focus is on how to represent the edges, because graph algorithms focus on traversing the edges of the graph. There are 4 ways of representing the collection of edges. Edge lists, adjacency maps, and adjacency matrices. Edge lists, which are an unordered list of edges or an unordered list of pairs of vertices, since a pair of vertices denotes an edge. Edge lists are a very common way in which the pairwise relationships are given as input in interview problems. So you'll be given a collection of objects and a collection of pairwise relationships in many cases. But edge lists are not convenient to work with from a time efficiency perspective. And so the first thing we often do in the code is to transform the edge list into an adjacency list. So an adjacency list tells you instantly who all the adjacent neighbors of a given vertex are. For example, in this graph, vertex 0 has vertex 1, vertex 6, and vertex 8 as its neighbors. And so we list those neighbors in no particular order in the adjacency list for vertex 0. One of the problems with a list, though, is that if I want to find out whether vertex 8 is present in the adjacency list for 0 or not, I have to sequentially scan the list to check if 8 appears anywhere in it. But if I organized the neighbors of 0 not in a list, but in a hash table, I would be able to instantly tell whether 8 is a neighbor of 0 or not, because all three of these neighbors would be found in the hash table. So when the neighbors are stored in hash tables instead of lists, we call the resulting structure as an adjacency map. Adjacency maps can always be used in place of adjacency lists, but they are especially useful when there is a chance that your input data has duplicate relationships. We don't want to add the same edge multiple times, and adjacency maps allow us to instantly check whether a relationship already exists in the growing edge representation or not. If it already exists, then we don't add the duplicate edge. Otherwise, we add it in. You can't instantly tell whether an edge exists in an adjacency list structure. And so adjacency maps, using adjacency maps is one of those tips that you won't get from an algorithms book, because algorithms books tend to assume that hash tables have a theoretical worst case complexity that is linear in the size of the table. In an interview, though, you're allowed to assume that hash table operations will almost always practically run in constant time: insert, search, and delete. So just like you're allowed to assume that quicksort will practically run in n-log n time, you can assume hash table operations will run in constant time. The probability of encountering the theoretical worst case is practically negligible. Adjacency matrices are basically two-dimensional tables which also tell you instantly whether an edge is present or absent from this representation. For example, if I want to find out whether 8 is a neighbor of 0 or not in the graph, I just need to look at row 0 and column 8. And if that's a 1, it means the edge exists. Otherwise, if it's a 0, it doesn't exist. For most real world graphs, if we were to build out such a table, most of the entries in it would be a 0. So this is not a space efficient representation. Adjacency lists and maps effectively store only the ones in the table. That is, they only store the actual neighbors for a vertex. And so they are more space efficient for real world graphs. And so whenever you're building a graph in an interview, you will most likely be building either an adjacency list or an adjacency map. Both of them are useful in quickly telling us, given a vertex U, what other vertices does it have a direct relationship with? And if you want to find out, given two specific vertices U and V, do they have a direct relationship or not? That is something an adjacency map does quickly in comparison to an adjacency list. But more commonly, interview questions on graphs will require you to detect indirect or long distance relationships. So in this diagram, S is not directly related to V, but it does have an indirect relationship with V since it's connected to V through this intermediate vertex U. So one can ask, given a vertex S, what other vertices does it have an indirect relationship with? And given two vertices S and V, do they have an indirect relationship? So to answer these, we can't just look up an adjacency list or a map, since we're talking about long distance relationships. We need to find a way to explore or traverse the graph starting from some source vertex like S. and we need to find all reachable vertices from S. So that leads us into module 3, where I explain how a general graph traversal algorithm works. Even students of computer science often miss the fact that all the standard graph algorithms you see here in this row are essentially minor variations of one single graph traversal algorithm. If you understand this general graph traversal algorithm, you are on your way to understand all 6 of these algorithms. So let me give you the gist of this general graph traversal algorithm. And I'm going to do that by taking the example of a small directed graph and show you how to explore it. So it's a directed graph. You can see that the edges here have directions. So think of them like one-way streets. So let's say we start our exploration from vertex 1, since we want to figure out which vertices are reachable from there. So vertex 1 is our source vertex. Now you can see by visual inspection here that this isolated vertex 6 and this vertex 7 are not reachable from 1 because you can't go against the direction of the arrow. But all other vertices are reachable. But in general, we want our algorithm to run on graphs with hundreds of thousands of vertices. We can't use visual inspection there to answer such questions. So we need an automated way to traverse such a graph and answer the question, which vertices are reachable from vertex 1? To show you how a general graph traversal algorithm works on this directed graph, I'm going to use a visualization. I will imagine that each vertex of the graph is like a fish swimming deep inside a blue ocean, shown here on the right. And I'm going to think of myself as a fisherman standing on this yellow beach sand on the left-hand side, holding a fishing net in my hand. Now, when this whole process starts, I do have one fish that is already given to me as reachable, and that is the source vertex. Now, since I can reach that source vertex, I'm going to imagine that it is already trapped inside my fishing net at the beginning when this whole process starts. So in the initialization phase itself, this vertex 1 is already inside my fishing net. This black circle represents my fishing net. So I'm going to pull this fish out of my net and bring it ashore. What's great for me is that this fish has hooks or direct relationships or edges connecting it to a bunch of neighbors, which so far lay undiscovered in the ocean. But now I can catch sight of them by looking across these hooks, and I trap them inside my fishing net. So notice in the graph, for example, that vertex 1 has outgoing edges to vertex 2 and vertex 5 in the directed graph. So these vertices have now been discovered via these hooks and are now reachable by me. So now I have 2 more fish inside my fishing net, and I choose one of them arbitrarily for now, and I pull on the edge going to it to drag it ashore. So let's say I pick vertex 2 and I pull on this edge and I drag it ashore. I place it on the sand, and I have an edge now from fish 1 to fish 2, indicating that it was the edge from vertex 1 to vertex 2 that I pulled on to drag vertex 2 ashore. Now I look at the outgoing edges from vertex 2 because I can discover new fish using them. So notice in the directed graph that vertex 2 has 3 neighbors in the graph, one of which is vertex 1, but vertex 1 already lies on the sand next to it, so you can ignore it. But the other 2 neighbors, 3 and 4, I didn't know they existed until now. I catch sight of them and I trap them inside my fishing net. I then pick the next fish that I'm going to drag ashore, And again, I'm making this choice arbitrarily here. So I'm dragging the fourth fish out by pulling on this edge from 2 to 4. Now, since 2 pulled out 4, I have an edge from 2 to 4 on the sand. I then look at the neighbors of 4, the outgoing neighbors in the graph, to check if I can discover any new fish. But 5 is the only neighbor, and 5 already lies trapped inside my fishing net. So there are no new fish that I discover which I can trap. So I then decide to pull another fish out of my bag, let's say fish 5. I pull it out by tugging on this edge from 1 to 5. 5 is dragged ashore, and the edge from 1 to 5 indicates which edge was used to pull 5 out. Notice that these edges seem to be forming a tree here on the left. Anyway, I next look at who the outgoing neighbors of vertex 5 are. And the only neighbor of 5 is vertex 4, which already lies captured on the sand. So I don't have any new discoveries. So there are no new additions to my fishing net. At this stage, I have no choice but to pull out this lone vertex that lies inside my net. I pull on the edge from 2 to 3 and drag 3 ashore. When I look at the outgoing neighbors of 3, I see a 4, but 4 already lies next to it in this tree. So there are no new discoveries, no new fish that I discover in the ocean. My fishing net at this stage lies empty. So at this point, I have no way to capture more fish, even though there are a couple of them still undiscovered inside the ocean, but I can't reach them. And notice that these are the 2 vertices which I could not reach from vertex 1. So let's look at the result of this graph traversal. The first thing that we can note here is that on the beach sand, we got a search tree. The root of that search tree was the vertex, the source vertex from where we started our exploration. The second thing to note is that the vertices in this tree are precisely the set of vertices that are reachable from S. In fact, every single vertex that was reachable from S lies somewhere inside this tree. The third thing to notice is that if there was a vertex, let's say C, which was pulled out of the bag by vertex P, that means we tugged on the edge from P to C to drag C ashore, then P is the parent of C in the search tree. So for example, why is 2 a parent of 3? Because we tugged on the edge from 2 to 3 to drag 3 ashore. I want to now be more precise about what I did by writing it down as pseudocode. So I'm writing a function for doing a general graph traversal starting from some source vertex S. And initially, all the vertices lie undiscovered inside the ocean. Except for the source vertex S, right? So what I do is I initialize an empty bag or fishing net, and then I put this source vertex S in it. I mark S as discovered. I will now repeat the following. As long as my bag or net is not empty, that is, as long as there is a fish still trapped inside the net, I'm doing something. What am I doing? You may recall that I'm picking some fish to pull out, and I made that choice arbitrarily. I tug on an edge to pull it out. I place it on the sand where it becomes part of this growing tree. And then I check its outgoing neighbors. And I'm going to do that by looking at the adjacency list for that vertex, or the adjacency map for that vertex, which I assume has already been built before we are executing this function. So if I see that there is a neighbor in the adjacency list which still lie undiscovered, I discover them and I add them to my bag or net, and I keep going, right? I keep looping around like that. So when we look at an arbitrary point in the execution of this algorithm, I will have a bunch of captured vertices on the left, which are part of this growing tree. I will have a bunch of discovered vertices on the right, some of which are trapped. Actually, all discovered vertices here are trapped inside my fishing net or bag. And there are others which still lie undiscovered. So in the next step, I will pick an arbitrary vertex from the bag. Let's say I pick this vertex U. And I'm going to pull it out by tugging on some edge leading to it. So let's say I tug on this edge from P to U, pull U out. P is part of the tree, which means there is a sequence of tree edges from S to P, right? So this path could have a bunch of vertices. So I pull V ashore, I add U, I pull U ashore and I add U to this growing tree on the left. And so now there is a sequence of tree edges starting from S and reaching U. So let me ignore the other vertices in the tree for now. I'm just showing you that U lies somewhere inside this growing tree. I then look at the outgoing neighbors of U in the original graph. Some of them might already be captured and lie on the beach sand. Some of them might have been discovered, but are still lying inside my fishing net. But what I'm interested in is, are there any neighbors that are still undiscovered? There may be a couple of them that are still undiscovered. Let's say V and W. If there are any undiscovered neighbors of U, I'm now discovering them. So I grab them and I add them to my bag or net. And I keep doing this over and over and over until at some point my bag becomes empty. And I exit this while loop at that point. So notice that in the course of execution of this algorithm, each vertex except the source vertex started out undiscovered. At some point, the vertex was discovered and added to the bag. And then there came a point when this vertex was pulled out of the bag and moved into the search tree on the left. So the typical life cycle of a vertex is that it's initially undiscovered, then discovered, but still lying inside this bag. And then it's pulled ashore and captured inside this growing search tree. So how do we maintain this collection of vertices in the bag? So if we use, depending on what data structures we use to represent the bag, we get different graph traversal algorithms. So if I use a first in, first out queue to store the vertices in my bag, the algorithm I get is breadth first search. If I'm storing the vertices in a last in, first out stack, then the algorithm would be depth first search. If I'm using a priority queue to store the discovered vertices. Then at the time of discovery, each vertex is going to be inserted into the bag with some priority value. And the vertex that is going to be pulled out of the bag next is going to be the one with the highest priority. Here, if I'm using a first in, first out queue, the vertex that I'm pulling out is basically the first vertex that was added in. In depth first search, the vertex that I'm pulling out is the last vertex that was added in, or the most recent vertex that was added. So when we are using a priority queue, depending on how the priority is defined, we are going to be pulling out a different vertex. And depending on how we define the priority, we get different algorithms, different advanced algorithms, like Dijkstra's algorithm or Prim's algorithm, or best first or A star. So all of these algorithms are variations of this general graph traversal algorithm. Now, since BFS and DFS are specifically considered important for an interview, right? Recall the quotes from Google, Facebook, Amazon I had shown you at the beginning. In our graphs curriculum, we next zoom into breadth first search and depth first search in more detail. In breadth first search, we explore the graph in concentric waves out of a source vertex, much like how a disease might spread out from a source in a population. In depth first search, we explore the graph one path at a time, going deep down a path and then retracing our steps back when we hit a dead end, and then trying some other path. So we divide our coverage of breadth first search and depth first search into 4 quadrants. Breadth first search on undirected graphs, depth first search on undirected graphs, breadth first search on directed graphs, and depth first search on directed graphs. The search trees that you get for these 4 cases from the same code for these 4 cases are different. They have different properties, which is why we want to distinguish them and separate them out into these 4 cases. And we look at undirected graphs first, because the breadth first search and depth first search trees on undirected graphs have simpler properties. I don't have time to explain what the breadth first search tree looks like, but just want to show you an example of it here. This is a breadth first search tree where all the edges in the original graph on which we did the traversal have been shown. The edges that make up the tree, recall the tree on the beach sand, those edges are called tree edges. And the remaining edges, if I take all the remaining edges in the graph and I add them in, representing them as cobwebs, so to speak, these remaining edges are of a second type. We call them as cross edges. The depth first search tree that is built by doing depth first search on that original graph also has tree edges, making up the backbone of that tree on the beach sand. The remaining edges of the graph appear as back edges, which connect descendants to ancestors in the tree. It doesn't matter which undirected graph you explore. At the end, if you used breadth first search to traverse the graph, you're going to get a breadth first search tree with tree edges and cross edges. And if you used depth first search to traverse the graph, you're going to get a depth first search tree with tree edges and back edges which look like this. Once we know the properties of a general breadth first search and depth first search tree, we can then think of building a separate breadth first search and depth first search tree for each piece in the original graph. The original graph may not be connected overall. It might come in pieces, which we call as connected components. So when we try to explore the graph by starting from some source vertex, we can only explore the piece that the source vertex was in. The vertices in other components are not reachable. So we have to launch a separate graph traversal for each connected component if we want to explore the whole graph. And one of the popular interview questions is to find all the connected components of a general undirected graph, which is given to you as input. So that is nothing but the number of connected components is nothing but the number of times we have to launch our graph traversal algorithm to explore the whole graph. Now, since a general graph traversal algorithm requires us to launch breadth first search or depth first search multiple times, we give students a template or a coding pattern for a general BFS or DFS problem. I don't have the code itself here, but I have the names for the three parts of the coding pattern. In the first part, you have to build the graph, which means you have to build the adjacency list or the adjacency map for the graph. And we have a piece of code which does that. The second part of the code requires us to write breadth first search or depth first search as a function. Why as a function? Because we may have to launch it multiple times to explore the whole graph. The third part of the code is what launches breadth first search or depth first search as many times as needed until every single vertex in the graph has been discovered. So these three pieces of code, which form our coding pattern, appear over and over and over in almost every graph problem. More complex graph problems will need you to add some extra lines to that code, but the lines making up the basic coding pattern are stable. This makes it easy to write code for any BFS or DFS problem because you already know what lines make up the basic skeleton. You only have to focus on filling the remaining lines in, the additional lines, which are generally not that many. For example, if the interview problem is about detecting cycles in an undirected graph, you just have to take the coding pattern, the basic coding pattern, and add a couple of lines to detect a cross edge if you're using breadth first search, or a back edge if you're using depth first search, because cross edges and back edges, depending on what tree it is, always indicate the presence of cycles in an undirected graph. We then look at more complex problems on undirected graphs, like detecting whether a graph is bipartite or not. And for many of these problems, you can use either breadth first search or depth first search, but you have to be familiar with the breadth first search tree and the DFS tree to know how to use their properties to answer the given question. So you have to map the given question to some property in the tree, which you are going to detect in your code. So in either case, the code is just a few lines added on top of the basic coding pattern. There are some problems though, for which only breadth first search would work. For example, if you want to find shortest paths in terms of the number of hops in an undirected graph, you can't use depth first search. Only breadth first search gives you shortest paths. And again, the code is just a few lines added on to the basic coding pattern. There is a special category of breadth first search and depth first search problems in which you're given a two-dimensional grid. So you can decide that every cell of this grid will become a vertex, and there will be an edge between two vertices if those cells are neighboring cells in the grid. So that's how you might decide to model the grid as a graph. But you're expected to do something special for this subcategory of problems in an interview. The interesting thing about this subcategory of problems is that if I'm given the ID of a vertex, which will be the row and column number of that vertex, I can figure out from the ID itself who the neighbors are. Right? For example, the neighbors of this vertex with ID x comma y can only be x plus 1 comma y, x minus 1 comma y, x comma y minus 1, and x comma y plus 1, provided that these exist within the legal boundaries of the grid. So do I need to build an explicit adjacency list to tell me the neighbors? No, I can save space and avoid building an explicit adjacency list. Instead, I can just write a get neighbors function to whom I give a vertex ID, and it will return me all the valid neighbors of that vertex. So we can represent the edges of the graph in an implicit way by having a get neighbors function instead of building an explicit adjacency list. And this approach saves us space without sacrificing time. And even marking vertices as discovered or not can be done within the input grid instead of having a separate array. So let me illustrate this by taking the example of a popular interview problem called the flood fill problem. So in this problem, you are given a two-dimensional image, which is basically a 2D array of pixels. Each pixel is represented by an integer value, and the value represents the color of that pixel. You're also given the coordinates of the starting pixel. This is the starting pixel in this example. And you're given the value of a new color. So the color of this pixel was originally white, and the value of the new color is a green. And you have to implement a flood fill operation. And by that, what we mean is you have to look at all the white cells that are connected to this original cell and color them all green. So this corresponds to the common operation in Paint software, where you decide what color you want to fill a particular region with, and then you tap on a particular pixel, and then when you do that, that entire region gets colored green. So I don't have much time left right now. So otherwise, in the class, we often give like a few minutes of time to students to think, and we have a lot of discussion before we finalize what algorithm we want to use. But in this case, either breadth first search or depth first search would work. And we can, let's say if we use breadth first search, we can actually see a parallel between the pseudocode that I had already written and the code that will actually get written once we implement breadth first search. So for each line that I had in the original pseudocode, there is a parallel line where I am not looking at a general bag. I'm specifically looking at a first in, first out queue. I mark S as discovered. And in the case of 2D grid problems, you need not have a separate array that tracks which vertex has been discovered or not. You can actually change the input cell in the grid itself to mark it as discovered. And while the queue is not empty, we pull out one of the vertices that's equivalent to popping the queue. And for each neighbor of that vertex, and this is where we call the get neighbors function. So normally we would look up the adjacency list of this vertex U to check each neighbor. In the case of 2D grid problems, we call this get neighbors function, which returns to us a list of neighbors. And if the neighbor lies undiscovered, which is equivalent to saying if the neighbor still has the old color, then we put the neighbor in the bag, we add it to the queue, and we mark it as discovered, which means we change the value of that cell to green. And so when we run this and we exit breadth first search, starting from this source vertex on which we clicked, so we call breadth first search with the coordinates of that starting vertex. When we exit here, this single breadth first search call would have painted or flood filled that input grid, and we just return that grid at the end. So this is the get neighbors function. Just leave that to you to think about. And sometimes there are edge cases that we worry about, like if the new color is equal to the old color, our code might go into an infinite loop. So that's something we have to be careful about. And we also want to think about why we use breadth first search. What if we had replaced the queue by a stack? Would it have worked? The answer is yes, it would have worked. I'll leave that to you to think about. What if the queue was replaced by a priority queue? Would it have worked? It would still have worked. But we won't use Dijkstra or Prim's algorithm or those other algorithms to do a flood fill, not just because they look a little artificial. In theory, we can use them, but adding vertices to a priority queue, removing vertices from a priority queue is more expensive than adding them to a queue or a stack. So we use breadth first search and depth first search for that reason. Now, having looked at a bunch of problems on undirected graphs, we next move to doing breadth first search on directed graphs, where the tree ends up being more complex. In fact, when we analyze this tree in the class, we often find that, we always find that we can't solve any sophisticated problems on directed graphs by looking at the BFS tree. We can only solve shortest path problems. And so we reserve BFS on directed graphs specifically for shortest path problems. And this is an example of one of the problems we look at in our class. given a snake and ladder game, which notice is again in the form of a grid, find the minimum number of throws required to win the game. So this is not an explicit graphs problem. We spend a lot of time thinking about why is this a graphs problem? How do we model it as a graph? How do we model it in a way that we can just plug and play the code that we already wrote for breadth first search? Finally, we move to depth first search on directed graphs, which is the most sophisticated, which leads to the most sophisticated kind of tree. And um, with small tweaks in our code, specifically for adding something called arrival and departure times, we can convert depth first search into a Swiss Army knife, which can literally allow us to detect all kinds of non-trivial properties about the graph, about the directed graph. So not only can we detect cycles, we can also sort the vertices from left to right in a way that the edges are only going from left to right if the graph had no cycles. So that's called a topological sort. Topology refers to the spatial arrangement. So if you want to arrange the vertices in a way that all edges go from left to right, that's called a topological sort, one of the most popular applications of depth first search. This, by the way, was the depth first search tree, fairly complex tree, which we spend a substantial amount of time in our live class on this. We also look at a modified breadth first search kind of algorithm called Kahn's algorithm, which is another way to do topological sort. And then we look at advanced applications of depth first search, like finding bridges, articulation points, and strongly connected components. The first two problems apply to undirected graphs. The third problem applies to a directed graph, and that's where we need to do the most sophisticated analysis of the depth first search tree, which gives us a very conceptual way to answer these problems. So this is what we generally do in the green section, right? The easier part of the graphs topic. I've shown Tarjan and Kosraju here, but increasingly, there are more and more questions being asked on them. So I would probably classify them today as part of the live class. Just to give you a quick summary of what we do in our advanced graphs modules, we consider what would happen if the graph was not a static graph, but if new vertices and edges were coming in dynamically. So if we want to solve problems, then we can't just keep resolving the same problem over and over every time a new vertex or a new edge comes in. We have to do something better. And that leads us to actually invent a new kind of data structure. Instead of using breadth first search or depth first search each time, we invent a new kind of data structure called a union find data structure. We optimize it so that it runs efficiently. That's the weighted union find structure. And we have a very neat optimization called path compression, which basically makes union find run in time that is, practically speaking, the same as breadth first search and depth first search. Not theoretically, but again, we're talking about an interview here where they practically run in the same time. So very often you'll find that there will be three ways in which you can solve many of these problems, either using breadth first search, depth first search, or union find. And the code for union find can often be smaller than the code for depth first search and breadth first search. So we have a coding pattern for union find as well. So for example, path compression is not something, the code for that is not something you'll find in an algorithms textbook, which you can use readily in an interview. There's a very efficient version of that code, which competitive programmers are normally familiar with. But again, that's why I said you have to combine both sides when preparing for an interview, the practical side as well as the theory. Now, union find is applied to a relatively sophisticated problem, the problem of finding the minimum spanning tree in a weighted undirected graph. So far, all the graphs that we were looking at did not have weights on the edges. But once you start adding weights on the edges, which could represent something like distances or costs for going from one vertex to its neighbor, then we can ask, is there a way to connect all the vertices together in a tree so that the cost of that tree, which is basically the sum of the weights of all the edges on the tree, to make that cost minimal. So for that, there is an algorithm called Kruskal's algorithm, which uses union find. But normally we ask students to come back to these advanced graph topics after they have done greedy algorithms and dynamic programming algorithms, because we don't want to memorize Kruskal's algorithm as a named algorithm. We want to understand how to design this algorithm. It so happens that the name happens to be Kruskal's algorithm, but we don't care about the name. We want to understand how it's designed. There's also another greedy algorithm for solving the minimum spanning trees problem called Prim's algorithm. And the code for this, again, is a small tweak of the code for breadth first search. In fact, again, algorithms textbooks won't give you the correct code, because in a practical interview setting, the priority queue library that you'll have to use to write your code does not provide you operations like decrease key or instant search, which are required to actually implement Prim's algorithm efficiently. So how do you bypass this constraint that the standard priority queue libraries don't provide you these operations? Well, there's a way, and we cover that in our classes for how to implement this quickly without compromising on the asymptotic time complexity. The same thing is done when we look at another type of popular problem on weighted graphs called the single source shortest path problem. And again, there's a greedy algorithm called Dijkstra's algorithm for it. The code for it is almost identical to the code for Prim's algorithm again. And again, the same issues arise here. You need to be able to implement this quickly without going through this, bypassing this constraint. So you have to implement Dijkstra's algorithm in a way that you don't use these two operations. And what if the weighted graph could have negative edge weights? Well, then Dijkstra's algorithm is not guaranteed to give you a correct answer. By the way, we go through the proofs for why these algorithms that we are designing are correct. This is important. Whenever you have a greedy algorithm, you need a proof. Otherwise, typically greedy algorithms don't tend to work correctly. So, but if you've done dynamic programming, then with negative edge weights, you can actually design a dynamic programming algorithm on a graph. And you find out at the end that it's called Bellman-Ford, but we don't care about that. For our purposes, it's a dynamic programming, the same dynamic programming strategy which we used on other problems. You can apply on graphs and get an algorithm which happens to have been invented by Bellman and Ford. And finally, the most sophisticated shortest path problems generalize the single source problem to all pairs, where for every possible source and every possible destination, you have to find the shortest path from the source to the destination. Now you can do this by running either of these two algorithms n times, where n is the number of vertices in the graph. But it turns out that there is a slightly more efficient way to do it. If you have sparse graphs, for example, there is a slightly more efficient way to do it called Johnson's algorithm, which runs also on graphs with negative edge weights, which Dijkstra's won't be able to do. So we can make Dijkstra's algorithm run on sparse graphs through a small tweak called Johnson's algorithm. And if the graph happens to be dense, which means there are a lot of edges in the graph. Sparse graphs are graphs where there are the number of edges is order the number of vertices. Dense graphs are graphs where the number of edges is order square of the number of vertices, right? Order n square. So there we again use dynamic programming, and we can reinvent this algorithm, which happens to be called as Floyd-Warshall. And finally, there are some optimizations like solving the shortest path problem by not proceeding purely from the source, but from the source and the destination. So doing a bidirectional search from both sides, which can improve the practical running time. And then there are finally algorithms that are small tweaks of Dijkstra's algorithm, which allow us to preferentially go in the direction of our destination. So if we have some kind of information available to us while doing Dijkstra as to how far we are from our destination, we can use that information to implement an algorithm which is called A star. A star is not typically covered in an algorithms course. It's covered typically in an intro to AI course, but we cover it as part of graph theory. And the code for it is actually a very, very small tweak of Dijkstra's algorithm. So it belongs to the same family. So with that, I would like to close this, end this presentation. So this again is a summary of all the topics that we have in our curriculum. Hopefully, they make more sense now. So I'm going to open the forum for some questions and answers. Since there are, let's see, there are more than 100 students, I won't be able to answer most of the questions. So we will continue some discussion on UpLevel. So operations, IK operations will send you an email with link to the discussion board where we can continue the discussion in case you have questions that I can't answer. A recording of this session will also be provided to you on UpLevel. You will also have access to our previous micro classes from earlier weeks. And again, IK operations will tell you how to access the discussion board to have discussions, follow-up discussions on this class. You can also sign up for our next micro class, which is going to be 2 weeks from now. So let me open the Q&A tab here. For some reason, I'm not able to open the tab. Steph, if you're there, is it possible for you to read out some of the questions?
Yeah, Omkar. If you go ahead and just close the presentation really quickly, or yeah.
Right. Oh, okay. On open questions. Is there a concept? So let me go top down. There was a question that required Tarjan's algorithm. So the thing is, you should not worry about names like Tarjan. It's really an application of depth first search, right? And I mentioned in this presentation that you have essentially 3 problems: bridges, articulation points, and strongly connected components, right? All 3 are advanced applications of depth first search. They all require a more sophisticated use of arrival and departure times, which I didn't talk about, but those 2 times are what make depth first search really powerful. And so if you understand how to use arrival and departure times to answer this question, that happens to be called as Tarjan's algorithm. And again, it's the same approach for all three of those problems. How do you handle this in a real interview? Well, if you haven't studied depth first search, advanced depth first search, it's going to be very hard. So these algorithms are typically studied in an undergraduate course, which is why I always tell students that it's a good idea to know at least as much as what, say, a sophomore at Stanford would know, right? So we do cover this in our program. So maybe you were not part of the program recently, so we have added these in. I read in a book that dynamic programming problems are essentially a variant of shortest path on DAG. Yes, actually in the pre-class videos on dynamic programming, I actually explained dynamic programming by precisely this approach, by showing how every dynamic programming problem is essentially a problem on a directed acyclic graph, where each subproblem that you're solving becomes a vertex, can be mapped to a vertex in a DAG, and then you have to solve each subproblem in a topological sort order. So that when you are solving any given subproblem, all the other subproblems it depends on should have already been solved and their solutions should have already been cached. Yeah, last year and some of the modules were not discussed. Yeah, you can ask operations about that. Let's see. Any other questions? Is there a concept like good enough code for an interview? No, so that's what I mentioned at the beginning, that you should not worry about micro optimizations. As long as you arrive at a correct and asymptotically efficient algorithm, it's generally good enough to be able to implement it correctly instead of worrying about micro optimizations. And one of the issues that you find in platforms like LeetCode, for example, is that they don't distinguish between optimizations that are required to improve the worst case asymptotic complexity and optimizations that are just going to incrementally improve the time complexity, maybe by a constant factor. Those are typically important in competitive programming contests, right? Those kinds of micro optimizations, but they're not important when experienced engineers are giving interviews at these companies. There are some exceptions though. There might be some problems where the interviewer specifically says that I want you to do this in one pass instead of two passes. So only in those circumstances do you worry about those micro optimizations. Otherwise, any code that runs in asymptotically, the best possible worst case time is good enough. In online interviews, are compilation errors a significant red flag? Not necessarily, right? So for example, just to give you an example, there was one student, he knew the code. He had learned how to detect bridges in an undirected graph. That's a very popular screening question at Amazon. But what he ended up getting was a question on articulation points. Now the code for articulation points is a little different from the code for detecting bridges. So he wrote the code for bridges. That code did not pass, but he was able to rationally explain, how exactly these arrival and departure times are being used to, detect packages that are going as far high up as possible. And the interviewer was able to see that he's able to make that conceptual progress, and he passed that interview even though the code did not compile. So it really depends on whether the problem is easy, medium, or hard. Articulation points are relatively hard to, they would be classified as a hard problem. It's not a problem on LeetCode, but still it's a popular question in Amazon. So examples like this are there. Can we do IK remote? In fact, IK is purely remote right now because of the COVID situation. So again, you can reach out to operations for details. Shouldn't you be also marked as discovered? Yes, well, at the time vertex U or any vertex was discovered and added to the bag, we need to mark it as discovered. But when we are talking about 2D grid problems, it turns out that you can use the input grid itself to store that information in some way that enables you to avoid using up an extra array, an extra two-dimensional array to mark which vertices have been discovered or not. What are some of the other graph algorithms? Well, I have all the graph algorithms that would be required in an interview in this presentation. So these are all that you need to know. In fact, if you are short of time, as I said, just focus on the green topics, breadth first search and depth first search. But if you really want to, be totally comprehensive, you could look at all these algorithms. What are cross and back edges? Yeah, I couldn't get the time to explain them. So those are edges other than the tree edges, which are added to the tree we got on the end on the beach sand, remember, where I just showed the tree edges. But if you take the other edges in the original graph, which didn't make it into the tree, if you add those edges in, those edges get classified as cross edges or back edges or forward edges, again depending on whether they go from ancestors to descendants, descendants to ancestors, or between two vertices that don't have an ancestor descendant relationship. The last category is what you call as a cross edge. Can you show us the syllabus page? Well, since the recording of this will be available on UpLevel, you'll be able to go back and look at the flow chart if you're asking about that. If you're asking about the overall syllabus for the program, you can reach out to operations or attend one of our webinars. Okay, so looks like we answered all questions. Are there any other questions? So thank you all for your time. And yeah, if you have any questions, feel free to sign up on UpLevel. We will have some follow-up discussions on this presentation. So I'll be able to answer more questions there. So Steph, do you want to take over?
Sure. Thanks everyone again for joining us today. like Omkar mentioned, we will be sending out an email to everyone that's joined. It'll have some instructions on how to join the discussion on UpLevel. And then to be able to learn more about Interview Kickstart, please join one of our webinars. You can see the sign up link on our website, interviewkickstart.com. You'll also find that link in our post email that we're going to send you all soon. If you have any other questions, we'll be happy to answer them on the discussion once we see you on there. All right, so thank you, Omkar. And thanks everyone for joining this evening. Hope everyone has a good rest of the night. Hey, Flora, I saw your last minute question here about having live classes at IK. All of our classes are actually live. So if you want more information about that, just join one of our webinars and you can find that on our website, interviewkickstart.com.